Here we go. Graphs, and in particular the terminology. So our learning goal is to understand the concept of a graph and to represent a connected network, as well as the associated vocabulary. And it's a reminder here that there are Lightboard videos, which is going to be just like this, except you can see my face and whatever. So graphs and graph theory is a new area of maths for you. So I don't want you to get any preconceived ideas here. I want to make it really clear to you that when we talk about graphs in Unit 4, we are not talking about statistical graphs. We're talking about graphs, which I'm about to show you now. This is going to be a really fundamental understanding of this stuff. So here's some information, and you might want to copy this diagram down, and I'll give you time to do that. I've drawn a graph there. I've deliberately picked this particular graph because it has an example of most things that you need to know. So we have 5 vertices, A, B, C, D, and E. So they're called vertices. In some places, they're also called nodes, but we'll be referring to them as vertices. We have 6 edges. So that's a light blue definition there. An edge is a connection between 2 vertices. So in this case, we have 6 edges. There's an edge between C and D. C and D are connected, but A and E are not connected. B and E are not connected. So you can start thinking about common examples of where you might have seen graphs before. For example, on maybe a road network, you could represent the circulatory flow of blood in your body through a mathematical graph, and then you can do stuff with that. So we apply this to contexts where your other subjects and other areas of work will be using them, but this graph theory is what creates the mathematical analysis of these situations. In green, I've written there this edge that goes from E to E. That's called a loop. It's got a very particular name. If it goes from a vertex to itself, it's a loop. And if you consider this like a road network, you could have a road that kind of circles back in onto a town. That might happen. Maybe people just live out in that road. So you have loops. I live on a road that's called a circuit, and ours is exactly like that. It just goes out and back, and people live on the circuit. So there's an example there. We have a definition here in pink of the degree of each vertex as well. So I'll write down some degrees. A has degree 0. Actually, I'll do it in pink so it matches. B has degree 3 because there are 3 edges that are connected to point B, to vertex B. D has degree 4, E has degree 2, and C has degree 2. So that's our information there. And let's talk about an example. Really, really easy example, which I've just given away 2 of the answers for. How many vertices are there? Hands. Don't let me down. 5, exactly. There are 5 vertices in this graph. A, B, C, D, and E are all vertices. How many edges are there? 6. Excellent. There are 6 edges. How many edges connect B to D? 2. Excellent. And what is the degree of D? And you'll notice here the notation. So we write degree brackets D. That's asking us to work out the degree of that vertex. If this was a road system, we might actually name them with town names. So you might have degree Beaudesert, and that you have to work out how many major roads go in and out of Beaudesert. How many edges are connected to that vertex? Yeah. Okay. And what's going to be really important today is as you listen here, as you collaborate in your table groups, and as you do the exercise, it's going to be really important that you are getting the language right. You need to know what's being asked of you in that Unit 4 exam when you are asked to determine how many vertices there are or something like that. The actual maths in today's lesson and for most of this term is pretty easy, but the language and the nuance in your descriptions is I'm going to roll on. I can see some people writing stuff down, but I can see most of them have also got the OneNote open in front of them, so I'm hoping that's okay. Here's some further definitions and languages. So this graph's a little bit more intense, but I want to make sure that you understand all these things. I'm only carrying my laptop around with me so the microphone's still there. So we have, in orange, first of all, you can have a subgraph or a cycle within a graph. So a cycle here would be that within this graph, I can go from B to C to D, back to B to C to D, and keep on going around that cycle. So a cycle is some way in a graph that you can get around in a circle, or whatever the shape is. B and D have edges. Now that's going to be important later on because there's going to be some definitions, certain types of graphs that can't have a certain name because they have multiple edges or they have loops or something like that. So you need to be looking and noticing those multiple edge situations. Any enclosed region on a graph is called a face. This will be really important when we get to Euler's formula in a couple of lessons. So this enclosed region is a face. This graph has three faces, three internal faces. It actually has four faces. The fourth face is the outside, everything else. So there is face at E, a face here, and then just the extra face, the stuff on the outside. A is called an isolated vertex. Again, in your Unit 4 exam, if I asked you to describe the vertex A and you said it was, a vertex that's by itself, we'd probably accept that. But what I need you to be able to do is if in the exam it says, state the name of the isolated vertex, I need you to know what's being asked of you. So it's an isolated vertex if it's not connected to the graph in any way. But you might also have a graph that's got two parts to the graph. So this is not the greatest example of this, so I'd have a look in the textbook at there. They've got a bigger graph. But this edge between D and E is called a bridge because we've kind of got a graph here and a graph there. If you took that edge away, you'd end up with two separated graphs. So if you've got any edges that if you took it away, it would separate the graph completely into two parts. That edge is sometimes referred to as a bridge, and it would, if it was removed, it would create a disconnection. And green, this graph is not a connected graph because A is isolated. So for it to be a connected graph, every single vertex has to be connected to the rest of the graph. In this case, A is isolated. If you remove that edge between D and E, then E would be isolated. Even though it's got an edge, it would be isolated. Yeah. Not really. Like technically, if I had an edge from A to B, and I remove that, that would be a bridge as well because it would separate the graph up. But in context, you're not really going to get anything where that's the situation. So your most common bridge is going to be one where you have this big graph over here and you have a big graph over there and they're connected by one edge. And that would be a bridge, but it can be anything where if you remove that one, it separates one group of vertices from the other group of vertices. There's no other connection. And that group of vertices could just be one. It doesn't have to have any edges. Good question. So this graph has four faces. Yep. Any questions? I've made this a really definition-based exercise. So you're going to find, as I've stated here, you're going to find a couple of things like cycles and faces aren't part of 11A, the first thing that you do. But I've brought some of those definitions forward so you've got them all in one place because I think that's a bit nicer. What happens, I don't think I've got everything, but I've got most things. What happens as we move forward, a few other definitions are introduced, so I wanted to help you get them all in one place. Here's a couple other things. Firstly, a simple graph is a graph that contains no loops or any multiple edges. So you might hear of a graph referred to as a simple graph. The hardest thing in this exercise is going to be remembering all these little nuances here. A complete graph has all vertices connected by an edge to each other vertice. So this graph up here is neither a simple graph nor a complete graph. A is isolated and it has a multiple edge and it has a loop. So it's not simple or complete. And a tree is a connected graph with no cycle. So if you have a look at my example above, or my two examples that are on the screen now, you'll see this is a tree, and we'll do a lot of work with trees. That comes later on. This tree here has no cycles. There's no way I can start somewhere and do a complete cycle and get back to the start. If I added any other edges, it would create a cycle. There to there would create a cycle, there to there would create a triangle, there to there, etc. Any other edge would create a cycle. In this case, this is a maximal tree. It's the most edges I can have without creating a cycle. So that's a tree. And here's another example. X, Y, Z, W is a connected graph because every vertex is included in the graph. It's a complete graph because all the vertices are connected by an edge to each other vertice. And it's a simple graph because there isn't any multiple edges or loops. It looks a bit like there might be a multiple edge, but in this case, WY is the only those two. And you can go WZY or whatever. It's complete because every single edge, every single vertex is connected to every single other vertex. Another thing you probably did when you were younger, or a lot of you probably did, where you get a circle, a bit like a clock face, and then you connect, and it makes a really nice pattern. You connect every, 12 to every number, 1 to every number, and you get this really nice pattern. If you haven't done it before, do it. It's really good. It's a connected graph and a complete graph because you connected every single edge. And lastly, directed graphs. So you could take this a little bit further, and I've done this example because it's actually an example I've just done with my specialist maths who are doing some work on matrices and applications of matrices. You could have directed and it could mean something else. So this graph has arrows. That means that Bobby is not connected to Andy, but Andy is connected to Bobby. This graph could represent a situation where they're all playing in a tournament, and so Andy beat Bobby, Bobby didn't beat Andy. And Aaron beat Andy, and Aaron beat Bobby, and Aaron beat Carlo, but Derek beat Aaron. So this is an example of a directed graph. It could be used to show somebody beating somebody else in a tournament. It could be used to show a lot of different things. It could be used to show a road system, but with a whole bunch of one-way roads, directional roads. So there's heaps of things it could show. The graph could represent the results of an arm wrestling contest. Is this graph simple, completed, connected? In this case, directed graph has definitions. So it's simple, there's no multiple edges. It is complete because every single vertex is connected to every other vertex, and it is connected. Sometimes in a directed graph, an edge is also called an arc. Another word for you. There we go. And I think lastly, yes, it is lastly. Lastly, if you take out a little bit here, which we talked about a bit earlier, we get a cycle, but in a directed graph, this is not really a cycle anymore because you can't go in any one direction around it because you're going against the direction. But it is called a subgraph. And so it could be taken out and redrawn, and we could redraw that as an equivalent subgraph. This is exactly the same as that. We don't really care. In mathematics, we don't care what the graph looks like. What we care about is what the graph represents. This graph represents Derek beating Bobby and Carlo, Bobby beating Carlo, and this graph here represents exactly the same thing. Doesn't matter how it's drawn. And an interesting little exercise on this is to go and have a look at like the Brisbane railway map's pretty good, but the most common example is the London Underground map, which is drawn not to scale. It's drawn based on connections rather than distances and directions and things like that. So you get on the London Underground, all you care about is if you get on at station A, you can get off at station F. If you actually get on, you might do this and this and this as part of the train trip, but on the map it's just a straight line with station B, C, D and E in between. And so that's graph theory. Those train maps are based on graph theory. You see it with the Brisbane map. It sort of suggests that you're travelling a perfectly straight line from about almost right up into Parkwood, which is not true, as you'll see if you go and have a look at the actual Google Maps of the area. So lastly, there's the resource, and here's the can you. And sorry, I've written 11A all over it, but it seems like it might be 10. Can you, 1, explain, define graphs? Can you define a vertex, edge, loop, connect graphs, face, cycle, degree, bridge, directed graph, or subgraph? Can you find a value or represent each element above? So it's a really heavy lesson on definitions. The actual mathematics is really easy. And my suggestion to you will be, don't take any time to try and memorize anything. Create your own definition sheet. Use mine as guidance, use the textbook as guidance. Have it there next to you. Do the work with that there next to you, and you will slowly learn it.